In this video, we will be looking at oblique asymptotes. So as a reminder, we know oblique asymptotes occur when the degree of the numerator is exactly 1 greater than the degree of the denominator. And the way we find an oblique asymptote is just by dividing the numerator by the denominator. And I do recommend you divide using long division because the denominator, of course, might not be linear, as in our second example on the right. Or if you're dividing by a linear and the coefficient of x isn't 1, synthetic division isn't as straightforward. So let's try to find the oblique asymptote for example 1. So I'm going to put my quotient out front, and here's my numerator. And now what times 2x would give us 4x squared? That would be 2x. And then we can distribute that 2x in. So 4x squared minus 8x. And then we can subtract. 4x squared minus 4x is 0, perfect. Negative 6x minus negative 8x is positive 2x. And then we can bring the 5 down. Now, what times 2x gives us 2x? Well, that's 1. And again, distribution. We'll have 2x minus 4. And now we subtract. 2x minus 2x is gone, perfect. 5 minus negative 4 is 9. And this is our remainder, but our remainder does not affect our asymptote. This here is our asymptote. Y equals 2x plus 1. Now let's try another one. Here we have a cubic divided by a quadratic. The degree is still exactly 1 more, so this will have an oblique asymptote. All right, so now, what times x squared will give me 3x cubed? Well, that's going to be 3x. And then I'm going to multiply that into all 3 terms. So that will be 3x cubed plus 3x squared minus 9x. And we subtract. So the 3x cubes disappear. Negative 4 minus 3x squared is negative 7x squared. 5 minus negative 9 is 14x. And then I'll bring the negative 8 down. And now what times x squared gives me negative 7x squared? Well, that's negative 7. And now I can distribute in. Now at this point, me distributing in is kind of useless because I know I'm going to get a remainder and it doesn't affect my oblique asymptote. But just to see. 14 minus negative 7 is 21x. Negative 8 minus 21 is negative 29. That's the remainder, does not affect our oblique asymptote. Our oblique asymptote is y equals 3x minus 7 from that quotient. So let's try to take this plus our previous rational functions knowledge and put it together in some graphing. And we're going to graph f at x equals 2x squared plus 5x minus 12 all over x minus 1. All right, so first thing, just like usual, we're going to start off by factoring. So when we factor that quadratic on top using whatever method you like, we get 2x minus 3 and x plus 4. Now we can see our x-intercepts, we can see our vertical asymptote, we can get y-intercept, we can get all of that stuff. And we see, because nothing cancels out, there aren't any holes here. So the x-intercepts are going to be 3 over 2 comma 0 and negative 4 comma 0 just by setting the numerators equal to 0 and solving for x. So I'll go ahead and plot those on my graph. While I'm with the x-intercepts, I'll find the y-intercept as well by setting the x is equal to 0. I personally prefer to go into my standard form because I know anything with an x will be gone. And then I'm just looking at negative 12 over negative 1, which is positive 12. But you can also look in the factored form and set those x's equal to 0, punch it into your calculator. So I plotted that. Now for my vertical asymptote, x equals 1 from that denominator. And I'll go ahead and draw that in. And normally we would do our horizontal asymptote, but because the degree on top is 1 greater, I'm going to find my oblique asymptote. So I'm going to do a long division here. So what times x gives me 2x squared? Well, that's 2x. So 2x times x is 2x squared. 2x times -1 is -2x. And we subtract. 5 minus -2 is 7x. And bring the -12 down. Now, what times x gives me 7x? That would be 7. So 7x minus 7. And our remainder here will be -5, which again does not affect the oblique asymptote. The oblique asymptote is y equals 2x plus 7. And when I go to graph that, I have to remember how to graph a line. The y-intercept is 7, so I'll put a little dot there. And the slope is 2, which means I'm going to rise 2, run 1 to the right. And then I'll continue that pattern. Now, I'm plotting the points gently because this is an asymptote, so our function isn't actually going through these values. It's just to get the sketch of the asymptote. And there we are, y equals 2x plus 7. And we might also want to find some key points here. My vertical asymptote is 1, so finding f at 0 and f at 2, one to the left, one to the right would be good. Now f at 0 we already have, it's the y-intercept. For f at 2, if I plug 2 into my factored form, I'll have 2 times 2 is 4 minus 3 is 1, and then 2 plus 4 is 6, 2 minus 1 is 1. So 2, 6. And now I have a general idea that I'm just going to follow the asymptotes. Something like this. Now I can also do my end behavior test and see what happens. So as x approaches infinity, so maybe I test the value like 100 or 1,000, and I would see that the number is very large and positive. So y approaches infinity, which is exactly what our function is doing over here. As x approaches negative infinity, and I plug in, let's say, -100 or -1,000, I'll see that I have a very large negative number, which is what this portion of the graph is showing. And then I could test around the vertical asymptote. So as x approaches, let's say, 1 from the right, and I plug in 1.01, I would get a very large negative number. So I'm approaching negative infinity, like I am doing right here to the right of the asymptote. And finally, as x approaches 1 from the left, and I plug in, let's say, 0.99, y approaches positive infinity. So let's try another one. We have a cubic function in the numerator and a quadratic in the denominator. For my denominator, I have no issues factoring. We'll have x minus 5 and x plus 2. For the numerator, since it's cubic, we are going to have to use our factor theorem and division to get that going. So when I plug in -2 into the numerator, I will get 0, which means x plus 2 is a factor. So I'm going to do synthetic division here, but you can do long division as well, of course. So bringing the 1 down, multiplying by -2, adding the terms, multiplying by -2, adding the terms, multiplying by -2, adding the terms, and there's my 0 remainder, which is great. So that means we have x minus 2 times x squared minus 7x plus 12. So now I'll go up into my numerator, put my x minus 2, and then factor the quadratic. So x minus 4 and x minus 3. And I just realized it should be x plus 2. There we are. And if we look at our numerator and denominator, the x plus 2's cancel out, which means we are actually just graphing x minus 4 times x minus 3 over x minus 5. But our restrictions are, of course, both on the 5 and the negative 2. In this example, unlike the other one, we actually do have a whole because the x plus 2's canceled out. So since I mentioned it, I will calculate the whole first. I know it's going to be negative 2 comma something. So let's figure out that y coordinate by plugging in negative 2 into the simplified equation. So negative 2 minus 4 is negative 6. Negative 2 minus 3 is negative 5. Negative 2 minus 5 is negative 7. So that's going to be 30 over negative 7, or negative 30 over 7. So I'll go ahead and plot that point. So negative 30 over 7 is 4 point something. So let's say right there. Okay. We also know we have a vertical asymptote at x equals 5, finishing up with that denominator there. So I'll graph that. We can also get our x-intercepts quickly from the numerator this time. So 4 comma 0 and 3 comma 0. I'll plot those, 4 and 3. We also can get our y-intercept by plugging 0 into the simplified version. So we would have positive 12 on top, negative 5 on the bottom. So I'll just put that like that. And that's negative 2.4. So there we are. And now we just need to see horizontal or oblique asymptote. If I look at either my original or my simplified, the degree of the numerator is 1 greater. And we can do our long division from the original, or for less work, I would say, the simplified version for the oblique asymptote. So I'm going to divide by x minus 5. Now, when I put the numerator on top, I will write it in expanded form. So x squared minus 7x plus 12. And now what times x is x squared? That's x. And multiply that x into x minus 5 and subtract your terms. And we'll have negative 2x and bring the 12 down. And now what times x gives us negative 2x? That would be negative 2. Multiply it in and subtract, and we get a remainder of 2, which again does not actually affect our oblique asymptote. So our oblique asymptote is at y equals x minus 2. So all of the important stuff here. Okay, so that means our y-intercept is at negative 2, and we're rising 1 and running 1. There it is. Okay, and we have quite a few points on this side, so I have a feeling I know what's going to happen like this. But we can also get some points to see what happens here to the right of 5, that vertical asymptote. So we already have f at 4 for a key point. It's just 0, but let's do f at 6. So that would be 6 minus 4 is 2, 6 minus 3 is 3, 6 minus 5 is 1, so 6 comma 6. Okay. And now, here we are. Just following my asymptotes. And I can do a double check with my end behaviors, of course. So as x approaches negative infinity and I plug in negative 100, let's say, I would get a larger negative number. So y approaches negative infinity. As x approaches infinity, I would plug in, let's say 100, and I will get a positive large number. So y is approaching infinity. As x approaches our asymptote of 5 from the left, I would plug in, let's say 4.99, and I would get a negative number. So y approaches negative infinity. And as x approaches positive, or 5 from the right, and I plug in, let's say 5.01, I will get a positive large number. And that would just be a check that I would go to my calculator and double check it so that things do match up. If they didn't, that would mean I did make a mistake somewhere and I could try to go and find it. And that's it for our oblique asymptotes.